I'm Wonchan from Stanford University, and also I'm working at Los Alamos National Laboratory as a summer intern. And I'll be talking about the Legion programming model. So I've been working on this project for 5 years, and actually this is a really exciting project. It's a very nice combination of HPC research and programming language research. And I'm very happy to have a presentation here about my work. Okay. So before I start, the whole project is joint work between multiple institutions: Stanford, Los Alamos National Lab, NVIDIA, and Slack. And our funding is coming from many sources, of which DOE is a major contributor, including the ECP program. And I guess you have already received an email that I sent out last night, right? So have you guys checked out the access to the cloud system? So we're gonna use our laptop to run simple examples that I prepared by ourselves. And you're gonna need shell and SSH. And you don't have to download all the examples from the cloud system because I already uploaded to the public repository, so you can take a look at it after the program. Okay? And before I move on, how many of you have ever heard of Legion before? Okay. And how many of you have actually written any program in Legion? Yeah. Okay. Oh, good. So this is a perfect cloud because the programs that I prepare is really simple. So for those of you who have experience in Legion, might find it very boring. Okay. So let me give you a high-level overview of what Legion is and what Legion tries to achieve. So Legion actually means two things. Legion is a name of programming model that we design, and also is a C++ implementation of the programming model. So this is a distributed system implemented in C++, so you can write a Legion application using our C++ API, but this is C++ and the runtime system, so the API tends to be really, really verbose, even though the core concept is pretty simple, I think. So because of the reason, we also made a high-level programming language called Regent. So Regent is a faithful implementation of the programming model, and we implement this language in Lua, which is a bit unusual because most compilers are written in C++ or C. And our Regent has an optimizing compiler, so if you write a vanilla Regent program, the compiler will generate an idiomatic Legion application out of your program.
So is there any particular reason you chose Lua for implementing that?
Yeah, I'll talk about it later. Yeah, okay. And because Legion and Regent share the same concept in the programming model, so I will just focus on Regent. But if you find yourself more familiar with the C++ API, then you can just write C++ API to achieve the same thing as in these examples. Okay? Okay? So one of our key design goals is to achieve sequential semantics of a program. So when you write a parallel programs in traditional programming models, you have to deal with two things. One is all idiosyncrasies of the underlying programming model. So if you have to write an MPI OpenMP program on some crazy system, you have to understand MPI programming model really well and OpenMP really well. And on top of that, you have your application logic you have to implement. So if you have any bug in your program, it's hard to tell whether that's from the logic itself or from some wrong use of the underlying programming model. So one of our kind of benefit of using Legion is that our programming model provides sequential semantics, which means that even though the underlying execution happens in parallel, you can assume that the program executes as if it executes sequentially, which allows you to do sequential reasoning of your program. So when something goes wrong, then you can just sequentially follow your program to figure out where the problem happens. Okay? And this is really important for productivity on modern hardwares, because current modern hardware is really heterogeneous and requires expertise in many different kind of programming models. And this also means that the runtime system will automatically extract the available parallelism in your program. This doesn't mean that we take a fully sequential program and somehow magically parallelize it. We still need some information about the structure of the program so that we can do a good job of parallelizing it. So I'll tell you more details about how you can actually structure your program in our program model. Okay? And the second design goal is throughput or handedness. So the post-Moore era, the individual processors are not getting any faster anymore. So the latency of a single job or single processor is not that important anymore. So it's more important to have like billions of work items ready in some place and fire them at the same time so that we can achieve the full parallelism available in the underlying hardware. And the last thing is that we intentionally make our runtime system fully dynamic. So all the decisions are made at runtime, and this is really useful to deal with the situations like machine crash or some frequency scaling for some unknown reason. And those things, if you want to kind of handle those kind of cases in a more static program model, you have to encode all those logic in your program itself. But in our program model, we have a mechanism and policy to deal with this kind of situations in a more graceful manner. Okay, so let me tell you a little bit more about throughput or handedness. So this means that we want to keep the machine busy. So what it means is that for every core, we want to put a full queue of independent work. And for every channel, we want to put a full queue of transfers. And we do it all the time. So this means that we need some sophisticated analysis at runtime on a program so that we can kind of look ahead what will happen in the program and schedule them in a way that we maximize the throughput in the program. Okay? And this makes some consequences. First of all, our program model, even though we provide sequential semantics, the underlying execution is very asynchronous, and there's no notion of like global synchronization or anything. So if you're familiar with the like traditional bulk synchronous style of programming, this might sound a little bit weird, or you may find it a bit unusual, but this is intentional. We want to minimize the synchronization between tasks to achieve the maximal throughput. So all the synchronization and communications happen locally whenever necessary. And this is our way to achieve sequential semantics with the support of underlying parallel execution. Okay? And this, again, means that you have to tell more about your program to the runtime system so that we can do the right job. Especially, you have to tell more about the structure of your data, how the data is partitioned or something like that, so that the runtime can recognize the dependencies between tasks and schedule them in an efficient way. Okay? So this is how our software stack looks like. So at the very bottom, we have Realm, which is an abstraction layer for different kinds of hardware. So Realm can abstract different types of processor, different types of memories, or different types of interconnects in a uniform way so that the layers above can ignore the differences between hardwares. And what Realm essentially does is quite similar to what Charm++ does or what MPI does. So the underlying program representation is fully explicitly parallel. So which essentially Realm just builds a task graph where the edges between tasks basically represent the dependencies between tasks. And on top of that, we have Legion. So Legion takes a program written in Legion program model and translates it into the distributed task graph at runtime. So Legion does all the dependency analysis, all the mappings of tasks, and finally generate an efficient representation executing on the distributed hardware. And on top of it, we have a Regent, the programming language. So the Regent program essentially is compiled down to the Legion application. And you see that Regent is wrapped around the Lua language. So Regent is actually an embedded language in Lua. So they share the same kind of environment, which is very unusual. And this also helps do the meta-programming of Regent programs pretty easily.
So when the user is writing a program, where are they writing it?
There are two entries here. So you can directly write a C++ application using the C++ API, or you can write a Regent program using our compiler. And actually, there are other options too. So for example, Los Alamos National Lab is building a framework called Flexi, which sits on top of Legion. So Flexi itself is a kind of implicitly parallel programming model. So if you write a program in Flexi, it will compile down to Legion and execute on Realm. And there are other DSLs that are targeting Regent. So you just write a program in DSL, and that will translate it into Regent and Legion, and eventually Realm. So. And the reason why we choose Lua is that Lua is very simple. There's only a table in the programming model, and it's sequential, and it's really easily embedded in any existing C program. And it's also very popular in the graphics community, so we chose to use Lua. And actually, the project also uses the embedded language called Terra. Terra is syntactic sugar around the LLVM-IR. It's a really easy way to use LLVM-IR. And what this framework provides is that you can generate a Terra program using Lua script. Okay? So essentially, our compiler is just a Lua script. And we just generate an LLVM-IR through Terra. And because we're using the full...
So that means we can write Lua programs in Regent as well. Does that mean that we can mix Lua and Regent?
Yeah, that's possible.
Okay.
But their execution might happen at different time. Right. So that's what I mean by meta-programming. So, yeah. Okay. And we actually use the full LLVM stack in our compiler. So that means you can import any C library in Regent, which is quite unusual compared to other programming languages. So as long as you have a C header that abstract some Fortran library, some C++ library, you can import it in a Regent program and use it. And in our opinion, Lua and Regent are pretty simple, have very simple syntax. So they're designed to be very easy to use. Okay? So let me actually try to show you how a Regent program looks like. So I'm going to connect to the server. Oh. Okay, so at the very first line, you have import Regent. So this is basically a Lua program. And we're going to kind of write a Regent program on top of Lua program. So this import means that I'm going to start using a new language, the new sub-language, in this case, Regent. So what this does is that the interpreter registers some custom parser, in this case, Regent parser. So whenever there are some Regent-specific keywords in the program, they will activate the Regent parser, and the Regent parser will do the code generation. Okay? In the second line, we have some table lookup here. So Regent lib is a table where you can find all the programming primitives in Regent. And Regent lib.c is a collection of all C headers, including send.library, send.io, or something like that. Okay? So I just rename it as C. So later we just use C.something to call some arbitrary C function. Okay? And you can do a similar thing. I'll show later, but you can just import some C header just like this. So local, some C header equals some special syntax. Then from that point, you can use a C function. Okay? And task is a keyword in our language. So task starts a new task, obviously. And in the body of this task, we just simply call the printf. Printf is from the standard C library. And it print out a simple string. And in the very last line, we just start the application, and we provide the name of entry task, in this case, main. So when the interpreter hit this point, interpreter will call the runtime to finish the code generation region, and it will start executing from the main task. Okay? Very simple. So I'll just do this. So the way you run this program is that we're using Torque. So you connect to the server, and you submit the script that we already provide. So you just qsub the script. So I'll do the same thing here. Qsub 1. Okay. Sorry. Okay, and it should be pretty quick. Okay, I already have an answer here, which is obvious. The answer is 42. Okay. Okay, let me move on to the second example. So again, this is kind of boilerplate that we have in almost every region program. And here we have some control structure. Right? So var is a keyword to declare a new variable. And here I provide a type in 64, but it's an optional. So the compiler will infer the type based on the value on the right-hand side. Okay? And here, the syntax is pretty standard, I would say. So you have block surrounded by do and end, and if else is traditional, right? And what this program does is to add up from 1 to 10 and print the result here. Okay? So far, so good, right? So I'm just skip the part. Okay, move on. Okay, let me tell you a little bit more about tasks. So tasks are a unit of execution in our programming model. So when you call a task, it doesn't push the task to the stack. It actually pushes to the scheduling queue. And later, the runtime thinks that the task is ready to execute. At that point, the runtime pulls that task and executes it on some parallel hardware. Okay? So when the task is scheduled on a particular processor, there is no preemption, except that the task gets blocked by something or it terminates. Okay? So you can assume the task will run to completion once it's scheduled on a particular processor. Okay? But tasks can block in some cases. And what do I mean by blocking? So blocking means that whenever task is waiting for something to happen, for example, it's waiting for some value to be computed by other task, it has to get blocked. Okay? And in that case, the task will be swapped by some other task that is ready in the queue. But and this is fine as long as you have enough work in your queue. But in some cases, if you have blocking in the task that is launching a bunch of other tasks, that will block the progress of your program because it cannot launch more tasks at that point, right? So you need to avoid blocking in any of your tasks that are launching other tasks. And like I said, tasks can launch other tasks called other tasks, and which we call subtasks. And this provides a nested parallelism. So if you think of a tree of tasks, there will be a first set of parallel tasks, and each parallel task can launch other set of parallel tasks. So this will build some kind of task tree. Okay, so So when we say a parent task is a task that launches other tasks. And when we say a child task, and it's a task that is launched by other tasks. Okay? Here's a simple example. So in this program, we have 3 tasks: summer, tester, and main. And you see that main launches summer and tester and print out the value. And the important property of main is that main doesn't actually look at the result of its child tasks until it hits the printf, right? So here, main task just gets a result out of summer task and pass it to some other task. And again, at this point, main task doesn't look at the value of sum. Okay? It's only when main hits this point that it actually needs to wait for something to happen. Okay?
What if you put a print statement between those 2?
So if you swap these 2, what will happen is that the main task will launch summer, and it waits for summer to finish, and then it will launch the tester. But if you wrote a program like this, then main task will launch summer and tester at the same time, and then wait for these 2 tasks to finish. So in terms of making progress, this way of writing program is more efficient because it will push all the independent jobs to the queue and just wait for something to happen. But if you swap these 2, then there's some other tasks that could be launched but are not launched because of the blocking. Okay? So key thing is that if a parent task inspects the result of a child task, the parent task has to block. So let me go back to my example. Here, we have a main task, which launches the summer task. And here, the main task inspects the value of sum, and it prints the value here, right? It's just a refactoring of the previous program, right? It's simple. If you run this, yeah, sorry. Okay, so you see that the summer is done, and then you got the main task print the value, okay? Because the main task has to wait for the summer task to finish. Okay, here's another example, which is the same, except that here the tester task launches another task, a subtractor, right? And actually, let me just follow the program. So in the main task, we call summer and tester, and like I said, these 2 will be launched and sitting in the queue, and then main task will be blocked at this line. And when the summer task starts executing, so summer will sum the value and return. And in the tester, you see that because we know that the sum value is greater than 40, the tester will launch the subtractor. And then it finishes. So if I run this program, we'll see that tester will finish before the subtractor finishes. Okay? Right? See? So the tester launches the subtractor, and then it finishes. And then subtractor will make the final value that the main task will print out. Okay? So this is a kind of asynchrony I talked about. So the underlying execution is kind of in a somewhat unexpected manner, but the programming model itself will still preserve the original semantics of a program. Okay?
Okay, so this is, trying to understand it. Okay. So you break your stuff up into 2 jobs, and then you split it up. So what would you do if you had, let's say, a regular loop, a glue loop, you wanted to write here? Then how would you break it up into two tasks for the system to work on? I'm trying to see how I can change my code to fit this model.
Okay. So if the body of your for loop has enough work to do, and each iteration is independent, then you can factor out the body into its own task and launch that task multiple times, and then the runtime will figure out that all those tasks are independent, so the runtime will run them in parallel, as long as there are enough number of processors. Does it make sense?
So the dependency of your functions, like how is it just based on the input of the functions? Like how does it know that?
Right. So I forgot to mention that. So here, the tester task is using the sum value here, right? So there's a dependency between summer and tester. So you saw that the summer always finishes before the tester finishes, okay? Because there's a dependency between the two. Okay?
But I have a question. Doesn't that make that there's a dependency with subtractor and tester? Because the tester's function subtractor?
Right, but tester already finishes.
That's easy for her.
Oh yeah. So let me.
Can you explain like the flow again?
Okay. So this is a bit interesting. So main task will launch a summer, and because the summer does not launch any other task, it will return a value and push it to the sum, right? And it will pass to the tester. And what tester does is it look at check whether the value is greater than 40, and it's actually greater than 40. So it launches subtractor, and then it doesn't do anything on the result, right? So it can't just return, right? So it just return the value. So here, conceptually, these two are two different values, right? The sum goes to the subtractor, and the result will be passed down to the main task. And once that part is done, tester can just finish.
How is the value passed along? I'm sorry, I'm trying to understand this. So the tester launches subtractor and then it can finish, right? But
right.
The output of tester depends on the output of subtractor.
Right.
So how does it know what value to return if it's finishing before subtractor? I might not be phrasing it correctly.
Right.
I think it prints before it returns, right? So I think you see tester is done, and then I guess it prints subtractor is done, and then.
So actually, what will happen is that at this point, I was incorrect. At this point, the tester will wait for subtractor to finish, to make the final value and return it to the main task.
So is there parallelism in this? Is there any parallelism in this?
No, it's just for demonstrating the core concepts here. Yeah, we'll get to that point later. So before I show you more interesting examples, I will explain about one of our tools called Legion Prof. So Legion Prof is a profiler for Legion applications and also Regent applications. And what this tool does is to provide an interactive visualizer of your execution. So if you get a timeline out of this, you will see one timeline per processor, and there will be multiple kinds of processors. And each time interval or each rectangle in that line correspond to one operation. And those operations are color-coded to distinguish between them. So the same kind of task is colored by the same color. Okay? And one important thing to note here is that if you see any white gaps in this timeline, that literally means that the processor was sitting idle. Okay, so the goal of performance tuning is to avoid any of those idle time or any of those white gaps in the timeline. So if you see any white gaps in the timeline, that means that there's something wrong in your program. If you follow the instruction in the slide, like I did, then you will have the timeline in this URL. So we map your directory to this URL so that you can easily navigate the profile result. Okay? So in my case, this is here. So I get prof now. So if you open up, then there's a summary of your execution. So each rectangular waves are utilization of your processor. So in this particular execution, so if I zoom in like this, there are many parts that I didn't do a good job, okay? Just because this program is too simple. And if I expand this, then you will see the actual execution of the program. So this is a main task, okay? And then main task launches a summer task, and summer task is running on different processors for some reason. And then there are some other tasks here, which I'll explain later. But anyway, so in this timeline, so the solid color means that means the interval that the task was actively executing. But if it sees any shaded part, these basically mean that tasks were blocked. So actually, this portion is when the main task was blocked, and you see a slightly different color here. Oh, sorry, here. This is when the main task becomes ready again. Okay, and if you want to know how to use this interface, you can enter question mark or slash, then it will show you the list of keyboard shortcuts you can use. And okay, I have another Legion prof example, and you can just follow the instruction and take a look at the prof. I will skip this part. And so far, I didn't explain anything about where the task should run, right? So the program itself doesn't tell where the main task should run or where the summer task should run. But for some reason in the timeline, those two are running on different processors. So the question is, who makes that decision, right? So in our programming model, we have a separate piece of code called the mapper. So the mapper chooses the target processor for each task and the target memory for each data item the task is using, okay? And every application must have a mapper. But that doesn't mean that you have to write a mapper from scratch all the time. So we provide the default mapper, which does some round-robin scheduling of tasks across available processors. So this default mapper works pretty well for most of cases, but it's almost certainly that you need a custom mapper once you start doing a serious performance tuning. So we provide a separate mapper API so that you can override the behavior of the default mapper, or you can write a mapper from scratch. Okay? I will talk more about the mapping in the later part of the slides. Okay? So now I talk about parallelism. Okay? Let's take a look at example 3. Okay? This is pretty simple. So in the main task, we are launching the printer task 99 times. Actually, the upper bound is exclusive, so it will iterate from 1 to 99. So there will be 99 printer tasks. Okay? And you see that each printer task is getting different I value. So all those printer tasks are independent. So that means they can run in parallel at the same time if we have 99 processors. Okay? So let's see if that's actually the case. So if you open the output file from the execution, you see that it was the main task that finished first, right? So what it does is it launches 99 printer tasks and it's just done. Okay? So this is how we make the progress of application as much as possible so that the runtime have enough independent tasks to analyze and schedule. Okay? And if you scroll down the output, the order of execution is non-deterministic because each printer task is independent, so the runtime can choose any task at any given time to execute. Okay? And
in this case, once it finishes the main task, does it go back and print the other numbers? Like, does that, I guess that thread would be idle, or does it help with printing the other numbers as well? So I wonder if, like, once you print main, does it sit there, or does it go back and print other things? Or maybe I'm understanding.
so actually that depends on how many processors you actually have in the system. So for example, if you have only one processor and you do this, then what will happen in the underlying runtime system is that once the runtime finishes the main task, it will go to each of the printer tasks and it print out the value, right? But if you have two processors, what will happen is that this main task will push all those independent printer tasks to both of the processors. So there will be like 49 independent printer tasks in each of the processor queue, right? And each of the processors will pull one printer task at a time to execute. Okay? This is really a different way of executing the parallel programs. So if I make a timeline, okay.
And how do you actually manage the resources? I mean, here you just do a kusub without telling him how much can he actually take. Let's say I do a kusub on best I takes the whole machine.
So the memory representation, the in-memory representation of tasks is actually very lightweight. So the memory usage for spewing out those tasks is not a big concern in most cases. But even in that case, you don't want to run your main task to completion to generate like billions of tasks, right? So we have, in the underlying runtime system, has a limit for how far ahead you can execute the main program and how many tasks you need to wait to see before you start analyzing them, and when the runtime has to go back to the original scheduling routine. So there are multiple parameters, but in most cases you don't have to worry about that because the memory footprint of the runtime is roughly like tens of megabytes.
Environment variables you can set to tell him the limits of what you can use. You have some like variables you can set to tell him the limits of resources you can explore. Just thinking as a parallel program, I may want to run a simulation on one core, one node, 10 nodes, whatever. Actually set this, or?
So most of these parameters are somehow. I should say that. Actually, the execution, the real execution on the distributed hardware happens on multiple runtimes. So each node will maintain its own tasks, right? So if you run your program, if you run your Legion application on like 100 nodes, then there will be 100 instances of the runtime. So each runtime has to maintain only some subset of tasks that it sees in its node. Okay? And what was the other question?
Can you just show us the rp3.sh file?
Oh, sure. Oh. Oh, yeah, I forgot to. So here I give a couple of arguments here. So the first two flags are basically activating the legion prof. Okay? And here we give some machine-specific parameters, right? So this LLCPU means that I want to use 4 processors in each of the node. And this LLUtil2 means that I want to use 2 runtime threads to schedule the tasks. Does that answer your question? Okay. Sorry. So I just made a timeline out of example 3. And you see that each of the printer tasks is running on a different processor in some random fashion, right? And they can run in parallel because they're all independent. Okay. So this is an example of for-all style parallelism. And I already said that main task finishes first and just spewing out all the independent tasks, right? And there's another example that's more interesting. So, okay. So in this case, the main task is launching printer task twice, right? But before it launched the printer task for the second time on J, it just flipped the sign of the value, right? So these two tasks are dependent on the same J value or same I value, but printer tasks for different I values can still run in parallel. So there will be like 99 chains of dependencies where each chain has 2 tasks. Does it make sense? So if you actually execute this program, even though the first printer task can run independent randomly, the corresponding second printer task should happen after the first printer task finishes. Okay? So it makes more sense if you see the output. So this time main task didn't finish first for some reason. Okay? And here we have task 1, and here we have task -1. So there's an ordering between these two tasks because there's a dependency. They're working on the same value. Okay? So, okay. Then you may wonder how we know for sure that the runtime does the right thing. How the runtime correctly finds all the dependencies between tasks, right? So for that reason, we provide another tool called Legion Spy. So Legion Spy is a tool to visualize the dependencies between tasks. And this is really useful to understand when certain things are serialized or there's any unusual behavior in the timeline that happens in the program. So let me actually generate a spy graph from example 4. Okay. Okay. So if you follow the instructions, then you will see event.pdf and dataflow.pdf. They are basically the same in the purpose of tutorial. So I will just click event. Okay. So you see that there's a strict dependency between 2 printer tasks here, right? So this one prints the positive value, and the second one prints the negative value. And there's no dependencies between 2 printer tasks of 2 different values, right?
So these dependencies are figured out automatically with the compiler, I'm guessing?
No, this happens at runtime. Yeah, go ahead.
No, do you handle global variables as well?
No.
Okay, so there's...
So in our programming model, you must not use any global variable, so that the runtime has control over what kind of data you're using in the task. Okay? And you see that here's an interestingly named task in between printer and another printer. Okay? So let me tell you what's actually going on here. So whenever you launch a task that returns a value, what will happen is that at this point, the runtime put the value to a future, right? So at this point, it does not get the exact value that printer is returning at this point. Instead, it makes a kind of handle that later you can retrieve the value, the real value, right? And the notion of future is not visible at the programming language level, and the compiler still does some code transformation to manage those futures. So what will happen is that in the first launch, you will get the future out of the first launch, and when the compiler sees -j, some unary or binary operator on futures, it will automatically lift those operators to their own tasks. So in this case, you have unary minus operator, so this will become a task that will read a future value and return a negative. It puts a minus sign on it. Okay? So that means that this minus is a task, and it will return a future, right? And that future will be passed to the printer. Okay? So that's why in the event graph or spy graph, you see this mysterious unary tasks. Okay? And the goal of this code transformation is to avoid blocking in the main task. Okay? So by doing this, we don't have to wait for the print task to finish before we can flip the sign. Okay? Good. So I think I'm not going to be able to finish the whole slide, but I'll be hanging around after the session and during the hands-on session. So if you want to finish the material, just come talk to me.
In this last example, which will be the final value of what was it, j? The variable. I mean, the final one is kind of not deterministic because the last task that gets executed will.
Oh, you mean the value of I?
Or j.
Of j. So when you exit this loop, j is not visible anymore because it's out of scope, right? So the final value of j doesn't really matter.
Let's say outside. Oh, okay, so there were a last task that executed.
Yeah,
you can reach the value after the.
Right. But if you move this j to the outside, that will change the behavior of the program. It will basically serialize the execution. Right? So for example, if you do something like, right, so here, I'm sorry. So here, we are trying to override the existing j value, right? So that means that the previous task should finish, right? Before you can move on, right? So you will see the last return value of the printer, the first printer task, okay? Right. So the usual development cycle is like this. We write a region application, and we run a profiler and see some white gaps or white spaces in the timeline. And we run Legion Spy to understand why they show up. So far, I talked about the individual values in tasks. But in the real application, you will want to manipulate a collection of data, right? Collection of data items. And region is our data representation to maintain a collection of data. So a region is a collection of data. It's typed which means that each entry has a certain type, but all the entries have the same type. Okay? And regions are basically a cross product of an index space and a field space. And an index space is basically a domain of point, and each entry in the region is associated with one point in that domain. And the field space is a set of fields that each entry has. So if you have like 10 fields, then each entry will have 10 different values. So you can think of a region as a multi-dimensional arrays of struct. Okay? So here's a very simple example. So this is a region where the field space has only one field bit, and the index space is one-dimensional because the points are from 0 to 9, right? So the set of points here is an index space, and you see that the entries have a Boolean values. So that means that this bit field has a Boolean type. Okay? So regions are our way to organize the collection of data and manipulate data in tasks. And I said the regions are kind of like multidimensional arrays, but actually regions can be also sparse. Okay? So in your index space, you may have some non-contiguous point, which is quite unusual. And you can have, in theory, any number of fields in your region. And you can have any arbitrary dimension for index space. But in the language, we only support 1D, 2D, and 3D, because those are the cases that people use most. Okay? And here, we make a big difference between normal functions and tasks. So far, the tasks just almost look like a function. But now, if a task takes some region argument, then a task must declare how it's going to use a region. Okay? And we call it privileges. Okay? So if a task has a read privilege on a region, then the task can read the value. And if a task has a write privilege, then it can write to the region. Okay? And this must be declared at the program so that the runtime system can do the dependence analysis at runtime. Okay? And there's a special kind of privilege called reductions. And reduction is an update through some commutative associative operator. And the difference between write privilege and reduction privilege is that reduction privilege actually can be parallelized. So if you have some number of reduction tasks on a region, those tasks can be actually parallelized. Whereas if you have 10 different writers to the same region, they should be all serialized. So the reduction privilege actually is quite common in test-based systems. Is a way to improve the parallelism of your program.
So what do you mean by that you can have arbitrary index spaces, but there's no built-in support for
arbitrary? Technically, what I mean by that is that so the index space is a template in C++. Okay, but we only instantiated it up to 3 dimensions in Regent. And if you're using the C++ API, you're fine. You can use any arbitrary dimension.
Oh, okay. Yes, but you can't do it in Regent.
Right, because there's no like template kind of mechanism in Regent. Okay, and one other thing is that the task can only perform the operations that it has privilege on, right? And that includes any subtask calls. So here, if you have only write privilege on a region and you want to launch some other task that tries to read the region, that's not possible. So that means the parent task has to subsume all the privileges that its child task can use on a region. So the privilege is kind of fully contained at the parent level. Okay? First of all, you see the new keyword f-space. So f-space means field space. And we define a new field space called bit field. And this field space only has one field, bit. And bit has a Boolean type. Okay? This is the same example that I showed you in the slide. Okay? And here, you see that now the task has a where clause because the task is getting a region argument, right? So the type of the region argument is a bit weird, but it's basically a cross product of index space and field space. So here, the region type starts with region, and it takes two arguments. The first argument is an index space, and the second argument is a field space. Okay? So in this case, I space 1D means it's one-dimensional index space. So if it's 2D, then I space 2D. Or 3D, then I space in 3D. Okay? And in the where clause, we declare the privilege on the region. So in the task, in this task, we declare the write privilege on the bit because we're going to write to the region, write to that field. Okay? So you see that the privilege not only takes the name of region, but also takes the name of the field. Okay? And inside the task, we actually update the bit field. Okay? And you see there's a construct for int, which is basically enumerating all the elements in the region, right? And this doesn't guarantee any strict ordering of the iteration. So if you want a strict ordering, then you have to use a different kind of for loop. And this is a way to give some freedom to the compiler and the runtime system to optimize.
So this is general for the for loops, like these for loops that we have seen in other examples.
You mean this?
Yes.
So we have two kinds of for loop. I have an example right down there. So, okay. So, in the printer task, it takes the same region, but now it declares a read privilege. So it only is gonna read the value of the field. And here, we retrieve the field bound. The bound is a special kind of field of a region which gives you the bound of your index space, basically. And using this limit, you can explicitly write a more general kind of loop like this, right? So you iterate from the lower bound, that low is a lower bound of the region, and you go up to the upper bound. And because this for loop is exclusive, you have to add +1 because the bounds are inclusive. And it prints the value. If the bit is true, then we print 1. And if it's false, we print 0. Okay. And finally, in the main task, we create a new region. Okay. So there's a bit of syntax overloading here, but the difference here is that we give the size of index space. Okay. So here the size is 10. So what this part means that I'm going to create a new index space with 10 elements.
So is this reads command, is that checking the privilege or declaring the privilege?
Declaring the privilege. And also checks the privilege at the compile time. So if you declare read privilege and you're trying to write to the field, then the compiler will complain. Okay.
So unless I'm missing it, so right under the print it says var limits is the bounds. So you're not defining what type of data limits is anywhere else? Like before, in the first example you did sum 864 equals 0. But are you defining limits anywhere? Or is it
so the types? So types are implicit or optional in our language, except for certain cases like task parameters or something like that. But in this case, the compiler will infer the type from the dot bounds. Okay, and dot bounds has actually type. So if I fully specify the type, it should be rect 1D. So int 1D is a point of one dimensions, and rect 1D is a rectangle of one dimension. Okay. So we create a region here and pass it to two tasks. And you see that this clear task is writing to the region, and parent task is reading from the region. So there will be dependence between these two tasks, right? Make sense?
What is a rectangle of one dimension? I cannot picture it.
What do you mean?
A rectangle of one dimension.
This is an interval.
So it's a line.
Yeah, it's a line.
Okay.
Rect 2D is the rectangle that we know.
Okay, so
3D is a cube, basically.
okay.
Yeah. Maybe we chose the wrong name, but yeah, it's fine. Okay. And here's another example. The first two tasks are the same, but here we have a blink task, which basically flip every bit in the region. And because we have to flip the bit, we declare both read and write privilege on the field. So this is perfectly fine to give multiple privilege on the same field. Okay. So in the body, we read the value and flip the bit and assign it back to the field. Okay. Okay. Let me quickly run this program. Okay. So you see. So here in example 2, we clear the bit and print the bits. So that's why we are seeing only zeros, right? And if you run the third example, okay. Now the bits are 1 because we flipped. Okay. And so I'm going to show you 2 examples that are almost the same, except one of the tasks is using reduction privilege in the second example. Okay. And this is to show you the difference between read-write or write privilege and the reduction privilege. Okay. So in the main task, we are launching inc task 5 times. Okay, so there are 1, 2, 3, 4, 5 inc tasks, and if you scroll up, then the inc task declares read and write privilege on the region. So what will happen is that all 5 launches of the inc task will be serialized. Okay, because the inc task is both read and write the region. So each inc task should wait for the previous inc task to finish to be able to read the last value on the region. Okay. So if I run this with a region spy, it will. Is it? Okay. So you see that all 5 inc tasks are serialized, right? So they run one after another. And that's because they're declaring read-write privilege on the same region. Okay. So now we take a look at the last example. So here, the inc task is the same, except that it declares the reduction privilege. Okay? So the reduction privilege also takes the operator that you want to use for reduction. So in this case, plus, right? And in the main task, we launch this reduction task 5 times. Okay? And we expect them to run in parallel. And let's see what really happens. Okay, so you see that, first of all 5 int tasks are run in parallel. So if there's no edge between tasks, that means there's no dependency. Okay? So all 5 int tasks are independent in this case because they're using the reduction privilege. But one thing a bit interesting here is that even the clear task doesn't have any dependence on these 5 tasks. And the reason is that whenever you use a reduction privilege, the actual reduction does not happen immediately. So the runtime will make a temporary instance that maintains the difference made by the reduction operator. And whenever there's a later task that tries to read the result of the reduction, then the runtime actually applies those deltas back to the original instance, original the memory allocation the reader task is using. Okay.
So is this not similar to the future thing that you told for the other example?
Yeah, in some sense, yeah.
So there is actually no future created in this example?
No, future is a completely different mechanism.
Oh, okay. So for some cases, a future will be created, and the task can actually take in a future and wait on it.
Right.
But for other instances, this delta kind of thing will happen.
Right. So if you're doing reduction on regions, then this will happen, right? But if
second question is that the regions copied by value into the task. Like if I pass say 100, if I launch 100 tasks with regions, will they get copied? Will the data get copied?
So actually, I was gonna talk about that point later, but yeah, I'll give you an answer right now. So the actual memory allocation for a region happens only when the task tries to read or write the region inside the task. So if the task just gets the region and passes it down to its child task, that task does not instantiate the region. Okay? So all the allocation, so even though you kind of create a region of billion entries, as long as you're not instantiated in any point in your program, that's fine. Okay? And actually we do that. We kind of potentially, hypothetically large region. And later I'm going to talk about the partition, but you partition the region into smaller pieces. So you kind of access individual pieces one at a time to avoid the instantiation of the big region. Okay? Make sense? So the key source of parallelism in any parallel programming model is data parallelism, right? So we talked about how we describe data in our program. So now I'm going to talk about how you partition the data to extract the parallelism out of it. Okay? So what we normally do in the task-based system is that you partition the region into smaller pieces, and you launch one task per piece. Okay? And that's the way to exploit the parallelism in the data. Okay? And Legion and also Regent provide a rich set of partitioning primitives because the extracting data parallelism is really important in our programming model. That's the only way to achieve parallelism, true parallelism in the program. Okay, here's an example. This is the same bit region. And let's say you want to partition this into 2 pieces. And the simplest way of doing it is to partition it into equal size piece, right? So here, each piece, or we call subregion, the subregion has 5 entries. And the set of subregions has a name, in this case, bit region partition. So we call partition as a name of a set of subregions. Okay? So in this case, there are 2 subregions, one colored with yellow and another colored with blue. And bit region partition 0 basically means the first subregion of this partition. Okay? So, and the reason why we give names to this partition is that we want to manipulate the partition in the program. Okay?
So where are these stored, these different colored partitions?
So the shape of partition itself is built as as a data structure called region tree, which I'll give you an example later. But the actual content of individual subregions will not be instantiated, like I said, until they are actually being used. This is the same example, except now we are trying to partition the region, right? So we create a bit region above, right? And here we provide the simplest possible way of partitioning the region, which is an equal partitioning. So the equal partitioning tries to partition the region into equal size subregions. And the syntax takes 3 arguments. So the first is equal, which means this is an equal partitioning. And the second argument is the name of region that we want to partition. And the last argument is a color space, which is an index space for colors. So basically, by partitioning, what we mean we give different color to each of the entries in the region and group the entries with the same color, okay? So if you look at the example here, so we give yellow color to the first 5 entries and group them into its own subregion. And we give blue color to the last 5 elements and group them into its own subregion. So right, so the color is basically a name of a subregion, and the set of colors is called color space. So in this case, we partition the region into 6 pieces because num pieces is 6. And this basically means that you partition, so for example, if you have two-dimensional space, two-dimensional region, and you want to kind of partition into tiles, then you will have a 2-dimensional color space. And here, like I said, we launch 1 task per subregion, right? So bit region partition is the name of the partition. And the dot colors gives you a color space, a set of colors you can use, right? So we retrieve 1 subregion at a time from the partition, and we launch the blink task. Okay? So there will be 6 blink tasks that are launched from the main task. Okay. Skip. Yeah. So a couple of things to note here is partitioning itself does not create a copy of the data. Okay, it just names a subset of data. Okay, it just describes how the partition should look like. So at that point, no data movement happens. Okay, and partitioning also does not destroy the existing region. Right. So the parent region and the partition can exist at the same time, and they can be used at the same time. If you look at the first example, some of the tests are launched on the region itself, and some tests are launched with the partitions. Okay, and regions and partitions are the first class object in our programming model. So you can create regions and partitions in tasks, and you can destroy them, or you can pass around to tasks, or you can stick it to the data structure. Okay.
Are these regions then contiguous in memory, or because I mean, if you're doing bitwise operations on something 60 bits long, that's not even a cache line.
Right.
You can't express at least you can't thread that parallelism. You can maybe use like a vector on that.
Right.
Or, I mean, does the runtime manage that and remove that parallelism, or does it try to express that and just route you all over?
So the shape of the region that the program perceives is different from the actual allocation of the region, right? And the way we achieve that decoupling is to linearize the points in the index space down to the actual address. Okay? So if you have a region and have a partition that partitions into 2 subregions where the first subregion is picking even elements and the other picking odd element, in that case, there could be multiple possible allocations, but most reasonable thing is to allocate a contiguous memory for each of the subregion, and there will be divided by 2 linearization from the original region down to the actual allocation. Does it make sense?
So if you were to go through the parent region and just start, to walk down in sequence, is there any guarantee on like stride for the accesses or?
Yes. And maybe we have to do this offline, but we have a language to describe the shape of instance. So you can choose either low major order or column major order or tiled order or something like that. You can choose which field should be contiguously allocated in the instance or not. Right? And that will give you exactly how the instance look like. Okay? And from that, you can retrieve the value of stride or which dimension you should iterate first or something like that. Okay? And this region and partitions are maintained as a region trees in the runtime system. So if you create a new region, it will start the new tree where the root node is the top level region. And you create a partition, there will be a node for partition, which basically represent a set of subregions, like this. Okay? And I only showed an example where you create one partition, but in theory, you can make however many partitions you want on the same region. So you could have multiple partitions like this, right? So you have bit region and you have 2 partitions, where the first partition partitions the region into 6 pieces, and the second partition into 3 pieces, right? And interesting thing is that anything you do on the first partition will also happen in the second partition. So conceptually, if you write through the first partition and try to read the value using the second partition, all the update will be made visible by the runtime on the second partition. Okay? And this is how we express the data movement between tasks. So to conclude, and Legion and Regent is a task-based programming system where the parallelism is implicitly expressed. And there are a couple of advantages of using Legion. First of all, you can easily exploit multiple-level parallelism by using regions and partition. And you don't have to worry about different kind of parallelism available in the underlying hardware because they are insulated by the program model. And for doing so, we provide a rich set of partitioning primitives, which unfortunately I couldn't cover. And we also decouple the description of a program from the actual mapping of the tasks to achieve a good performance portability. Okay? Thank you.